Unit 4, Applications of Derivatives, Subsection 3, Derivatives with Respect to Time. Okay, so there's a bunch of learning outcomes for this particular section. First up, I understand that in general, dz over dk represents the rate of change in z with respect to k, and can use this knowledge to solve problems where one quantity is changing with respect to another. We're going to see that here right away. I can solve problems where an object's area is changing with respect to its radius or time. I can solve problems where the object's volume is changing with respect to its radius or time. So we have area and volume going on. We can interpret information in the problem to determine which given quantities represent derivatives and what those derivatives are. So we're going to find now that the derivative is going to be the rate of change of something. If a quantity is changing with respect to time, then I understand that I will often have to use implicit differentiation with respect to time. So implicit differentiation is going to be huge for this section. I know the difference between a constant and a varying quantity, and know I must not replace a varying quantity with a numeric value until the derivative has been taken. We're going to spend a lot of time on that in section 2 and 3. And then the last one, I can find mathematical relations to describe the related quantities in a problem, and then take the derivative of that relation to ultimately solve a related rate problem. So we're going to have to make up a bunch of formulas on our own, and you'll have some starting points, but we're going to have to do some thinking as well. So part 1, rates of change. Okay, so if v is the volume of a function of time, and t is the time, then dv over dt is the rate of change in volume with respect to that time. So the important part here are going to be these little example things, like 30 liters per minute. So liters is a volume, minute is a time, so that is a rate of change. We are changing by 30 liters per minute. If v is volume and r is radius, then dv dr is the rate of change of the volume with respect to that radius. So say 5 liters per centimeter. Okay, so for every centimeter increase in radius, we gain 5 liters in volume. Okay, we can do this with cost. Okay, so if c is the cost of a function, cost as a function of n, and n is the number of items you purchase, then dc dn is the rate of change in the price with respect to the quantity purchased. Okay, and the last one, if n is the number of bacteria present as a function of time, and time is t, then dn dt is the rate of change in the number of bacteria with respect to time. So say like 30 bacteria per minute, something like that. Okay, so let's get started. Okay, so example 1. A spherical balloon is being inflated. The volume is changing with respect to the balloon's radius. Find the rate of change of a balloon's volume with respect to its radius when its radius is 15 centimeters. Now, you'll get a formula sheet with a bunch of these on, but for right now, what we need to know, okay, it's a spherical balloon, so that means it's a sphere, and the volume of a sphere, volume, is 4/3 pi r cubed. Okay, that's been a formula way back from grade 10. Again, not a huge deal. So what we're going to do, its volume is changing with respect to its radius. So really what we want is we want dv dr. Okay, so in this particular section, we're not going to use the primes very much. This is the Leibniz notation. Okay, so dv dr, so that is the rate of change of volume with respect to its radius. So we're going to use this notation a lot more. Okay, and we just take the derivative with respect to r. So the 3 comes down, so 4/3 times 3 is just 4. Okay, and then the pi just goes, and then of course the exponent decreases by 1. Okay, so there we have it. Okay, now when its radius is 15 centimeters, so we are going to take the derivative with the r there, and now see how the derivative has an r in it, so now we substitute that number. So dv dr, okay, so 4 pi and then 15 squared. Okay, so what we're going to do in a lot of these pi type problems is we're going to answer in terms of pi, so we don't typically type the pi into our calculator. So in this one, we're going to type in 4 times 15 squared. Well, that works out to 900 So dV dr equals 900 pi. Now, this is technically a centimeters. So the answer would be centimeters squared. But I want to go back to here because dV, so that's volume divided by radius. So volume is measured in centimeters cubed per centimeter. Now, if you cancel those units, you do get the centimeters squared, but this is more descriptive because the volume is changing by 900 pi cubic centimeters, okay, per centimeter of radius at that point. So even though it simplifies to centimeters squared, writing it the units like this gives you a better idea of what's going on. So again, the volume is increasing by 900 pi centimeters cubed for every centimeter of radius. Okay, so there's the first one. Okay, number 2. The population of yeast in a vat at a brewery after T hours can be approximated by N equals 18T squared plus 400T plus 500. Find the population of yeast after 5 hours, and then find the rate of growth after 5 hours. Okay, not a big deal. Okay, so the population, that's just N. So we want N at 5 hours. So that's going to be 18 times 5 squared plus 400 times 5 plus 500. Okay, so we just get our calculator out here. Nice and handy. Okay, and we just type. So, pretty straightforward. So, 18 times 5 squared plus 400 times 5 plus 500. Okay, so that is 2,950. Okay, so population, so that's just, okay, so yeast cells or bacteria, whatever, something like that. Okay, now of course, find the rate of growth after 5 hours. So that is dN dt. So that's the rate of change in the number of yeast cells or bacteria. Okay, so that's going to be, so we go back up to the equation here. So 18 times 2 is 36 T plus 400. Okay, so if we want that at 5 hours, we find dN dt at t equals 5. So we just go 36 times 5 plus 400, which equals 580 bacteria per hour. Per hour. Okay, so pretty straightforward. Sorry, yeast cells. Okay, but that's the idea there. So the first one was just the number of yeast bacteria. The second one is the rate of growth. Okay, that's that one. Number 3, the mass in kilograms of a blue spruce tree as a function of time for the first 10 years. So from 1 to 10, okay, is given by m equals that. So what would the mass of the spruce tree be at t equals 4, a 4-year-old spruce tree? Okay, so again, we're just going to use the formula they give us. So m equals 0.25, okay, times 4 cubed plus 0.3 times 4 plus 0.2. Okay, again, we just straight type that into our calculators, and we figure out that the mass of the spruce tree is 17.4 kilograms. Okay, pretty straightforward. Again, we're just typing into our calculator. The next one, though, says what is the rate of increase in mass? So that is dm dt. Okay, so dm dt, so we take the derivative of this. So the 3 hops down, so 3 times 0.25 is 0.75 t squared. Okay, plus 0.3, right? The t just, it's only a 1, so it doesn't do much. Okay, and then the 0.2, the derivative of 0.2 is nothing, so there you go. Okay, so there is our derivative, and now we want to figure that out at 6 years. So 0.75 times 6 squared plus 0.3. Okay, so again, we're going to just type that into our calculator, and what we end up seeing at 6 years old, the tree is increasing in mass by 27.3 kilograms per year. Okay, so that's what that means. The unit comes from here, dm, so that's the kilograms, divided by the time, and of course our time is given in years, so there you go. Awesome. Okay, and then the last one. Okay, a salt crystal is basically cubic in nature. In an 80% salt solution at 15 degrees Celsius, the dimensions in millimeters of the crystal are a function of time given by L equals 0.15 square root of t plus 1. What is the growth rate of the crystal after 12 hours? So growth rate, so we want dl dt. Okay, and so we take the derivative. Now that's got a square root, so we're just going to go back and rewrite this. Remember, a square root is just a 1/2 exponent. So we're going to write it like this because it's just better. Okay, so the half jumps down, so half times 0.15. Well, that is 0.075. Okay, so the half jumps down, and then we get t plus 1 to the negative a half. Now, that is in brackets, so we have to apply the chain rule. Lucky for us, the derivative of the inside is just times 1. So we could put that times 1, but it doesn't change anything, so we could ignore that if we really wanted to. It's not that big a deal. Okay, either way, we want the growth rate after 12 hours, so we could just put the 12 right into there. Now, because we're just substituting numbers, there's no reason we can't have the negative exponent. Usually we simplify this to something like this, t plus 1, okay, and then we put the square root back in, or just to the positive half, something like that. Either way, like we could type in our 12 hours into there or into this one. It really doesn't matter at this point. Okay, so when you do type it in, whichever one you type it into, you get 0.021 millimeters per hour. So the side length, or the growth rate of the crystal is, for the length of the side anyway, is 0.021 millimeters per every hour. Okay, that's it for this section. Talk to you later.